We're also going to talk about the high-temperature gas reactor. The high-temperature gas reactor, as the name implies, is cooled by gas rather than liquid. Typically, they're moderated by graphite, and they're cooled by either carbon dioxide or helium at moderate pressures, around 4 to 8 megapascals. You can use a two-loop Rankine cycle with a steam generator to transfer heat from the gas to the water for steam, or you can use a direct Brayton cycle to generate electricity. Now, the moderator here has a small slowing down power, so you're going to have a large moderator to fuel ratio and a low power density. And you have to have a little bit higher enrichment for this than you do for a typical light water reactor. Well, one of the other issues here is that gas is not a very good coolant. The heat transfer coefficient is much lower for gas than it is for liquid. So it requires a lot of flow recirculation, and there's a large temperature difference between the coolant and the fuel matrix. Now, this system operates at 900 degrees Celsius or higher, which is good because it provides higher efficiency, and the heat can be used for process heat for other processes. However, there are some materials challenges associated with this system. The liquid metal fast breeder reactor, as it sounds, is cooled by liquid metal, and they can be either pool type, like the diagram shown here. These are built in France, or for instance EBR2, or it could be a loop type. And loop type SFRs, our liquid metal reactors, have been built in England and Germany and Japan. So the liquid metal we use is usually either sodium, a sodium-potassium mixture called NaC, lead or lead bismuth, and the benefit here is that it can be a low-pressure reactor vessel, around 150 psi typically, which helps with the economics. And the liquid metal has a very high thermal conductivity, low neutron absorption, and a very large temperature margin for boiling. The fuel for these is usually like a mixed oxide or a metallic mix of plutonium and uranium. It's higher enriched than for a typical light water reactor, so we have to be aware of the possibility of reactivity excursions, and scram reliability is very important. The fuel pins tend to be around 0.6 centimeters in diameter, and they're wrapped with a small wire. That wire serves to maintain the spacing between the fuel rods, which are arranged in a triangular array inside of a hexagonal assembly can. This makes for a very compact core. No moderation is required because it's a fast spectrum reactor. So then, for this system, you would have to transfer the heat from the liquid metal to some secondary coolant to generate power, usually steam. For this reason, sodium-cooled reactors tend to use 3 loops to avoid the possibility of a sodium-water reaction damaging the primary system in case of a steam generator tube rupture. Finally, we're going to look at the molten salt reactor. Now, the molten salt reactor, the fuel itself is molten, which eliminates the possibility of a reactor meltdown. And that molten fuel is circulated through the reactor, which is mostly composed of a moderator. So when the fuel enters the moderated region, fission chain reaction occurs, and the fuel itself heats up, and then moves to a secondary heat transfer system, some kind of heat exchanger, that transfers that heat to the power system. So this is a very small system, which is very attractive for small modular reactors. It tends to operate at low pressure, and there's a lot of potential here for chemical separation of fission products and refueling while online. So there's a lot of promise in this design as well. Small modular reactors are a pretty recent development. Over the last few decades, people have been looking at designing very small reactors to use for microgrids and other systems. Westinghouse is designing a reactor. Initially, they were involved in the IRIS consortium, but they left to design their own based on AP1000 technology. We have a shortened core height here, but the RPV is still full height to allow for natural circulation during accident conditions. But the heat transfer behaviors are very similar. The only benefit here is that the heat generation is much less, which hopefully is going to make this easier to cool during accidents. NuScale is also designing a PWR, but this one is cooled entirely by natural circulation. There are no pumps. And so the power is only 45 megawatts electric per unit. It's still 80 feet tall to allow for the natural circulation, and both of these reactors have integrated the pressurizer at the top of the pressure vessel. So it's no longer attached to a loop, it's actually directly on the pressure vessel. And they have integrated the steam generator within the system as well. Last, we're going to talk about MSTR. So the Missouri S&T reactor is here at S&T. It's a research reactor sitting in a large pool of water, so we don't have any emergency core cooling or forced flow through the core. We mostly rely on natural circulation cooling. The fuel itself is in these square cans, so we're not going to have any mixing between the fuel elements. And the inside the fuel elements, we have this plate fuel. Now the plates are not flat, they're slightly curved, which is going to help increase the complexity of the heat transfer problem just a little bit. And then the plate fuel itself, we have heat generation in the uranium fuel, and then that uranium fuel is sandwiched between aluminum plates, which are acting as the cladding. And then we have conduction through the fuel and the cladding. Now, this reactor is a little bit unique because the thermal design limit for this reactor is actually the blistering temperature of the cladding, where it can start to deform and separate from the uranium fuel. So we have to be careful of that thermal design criteria when we're thinking about these types of reactor designs. The next couple slides here just contain a lot of properties of prototypic reactor designs, just generic or average reactor designs for each of the various types. So on this slide you can see there's some information about the fuel particles, the pin geometry, the assembly geometry, and so on. This next image, this next table, is going to show you some information about the reactor vessel, linear heat rate, power density, performance criteria, and so on. These two tables were taken from the textbook by Tadreus and Kazemi, Nuclear Systems 1, so you can find some more information there. Now, if we're looking at the energy generation term, or energy sources in a nuclear reactor, of course most of the energy comes from fission itself. Fission product kinetic energy and fission neutron energy, gamma radiation. We're also going to have some neutron capture, and then the radioactive decay of the daughter products, the fission products. So we're going to have some kinetic energy there from the daughters, gamma radiation, and we're also looking at some delayed neutron energy. About 88.4% of this energy is absorbed within the fuel itself. Another 2.5% or so is absorbed in the moderator. About 4.1% is absorbed in the structure, the cladding, the stainless steel structural components, etc. And about 5% is unrecoverable. It's neutrino emissions. Neutrinos don't interact readily with anything, so that energy escapes. So the total energy release is about 200 megaelectron volts per fission. And about 90% of this is immediately released. The rest is released later as the fission products decay, hence the term decay heat. In the moderator, the energy deposition is mostly due to inelastic and elastic scattering during the thermalization process. This actually decreases very rapidly with atomic mass of the target, which is why it's not very significant in structural components where the atomic masses tend to be higher. In the structure, heat generation is mostly due to gamma attenuation and gamma absorption. This is actually why there's a gamma shield in boiling water and pressurized water reactors. There's a metal can around the core, between the core and the pressure vessel, and the purpose of this is simply to absorb gamma rays so that we don't have direct heating of the reactor pressure vessel, which would cause some problems, especially when we start talking about natural circulation. Now, we also can use the hot channel factors to relate the maximum power to the average power. Now, in a reactor, the power profile generally follows the flux profile, so an analysis with MCMP or something like that can tell us the ratio of maximum flux to average flux in the radial and axial directions for a core, if the core is roughly cylindrical. So this can give us what we call the nuclear peaking factors. We also have some additional hot channel factors that account for manufacturing uncertainties in the fuel density, fuel enrichment, and the fuel geometry. There's some tolerance for those manufacturing parameters, so they may vary slightly from the optimum. We also have to look at the core flow behaviors. You can have coolant mixing between assemblies in a PWR, and in between the fuel cans, in a boiling water reactor where there's no fuel, there's some small gap in between the fuel bundles. You can also have mixing, especially in PWRs. Flows from the hot channel may be redistributed to cooler channels. Typically, these two factors are evaluated through testing or CFD rather than theory. This allows us to relate the average core power to our failure limit. Basically, the maximum core temperature is higher than the average. We use these peaking factors to find the hotspot temperature by considering the engineering uncertainties. There's an overpower factor that accounts for the possibility of reactivity excursions, and then that gives us our margin, our safety margin, which is our factor of safety for the core, the ratio between the failure limit and the design limit for a transient. The decay heat represents energy that's not produced by fission, but rather by radioactive decay. It varies depending on your fuel type. It's usually a little bit lower for plutonium than it is for uranium, and it's produced by the radioactive decay of fission products and also actinides caused when uranium-238 absorbs a neutron. Now, fissions caused by delayed neutrons can also occur, but typically they're only significant for just a few minutes after shutdown. If the operating time is more than a few days, the decay power becomes roughly independent of operating time. It's pretty much the same after that. You've reached an equilibrium condition. Now, when this decay occurs, almost all of the beta energy is deposited within the fuel, but only a small part of the gamma energy. Most of the gamma energy is absorbed in the structural components and then a little bit in the moderator. Finally, we have to address this chemical energy in nuclear systems. We have to concern ourselves with temperature limits because of this. If the cladding temperature gets too high, you can get this zircaloy cladding interaction. You can have sodium-water reactions for a sodium-cooled reactor. In gas-cooled reactors, we have to be careful about getting oxygen into the system because the graphite can oxidize. And then if the core does melt and you have a severe accident, you end up with this corium, which is a mix of molten core and cladding and structural materials. And if this is able to escape the pressure vessel and come in contact with the containment, the water and carbon dioxide released as the concrete decomposes because of the heat can actually oxidize some of the elements in the corium and release additional chemical energy. And then this leads us to the final thermal design limits. Now, most reactors have a metallic cladding, like boiling water and pressurized water reactors, sodium-cooled reactors, and so on. So the thermal design limits here are imposed to maintain the integrity of the cladding. An obvious criteria is that the fuel can't melt. But generally, the cladding temperature limits are more restrictive. In water-cooled reactors, it's to prevent the zirconium steam reaction. In liquid metal fast breeder reactors, we need to prevent boiling of the coolant. And we also need to prevent critical heat flux, which is a multi-phase flow problem. A high-temperature gas reactor or graphite-clad reactors have a little bit different fuel structure, and here the thermal limits are determined by the maximum acceptable fission gas release. So at low power or steady-state operation, we want to minimize the diffusion of the fission gases through the graphite casing. So the temperature limit is about 1300 degrees Celsius to minimize diffusion. And for transients, we're less concerned about the slow process of diffusion, and we're more concerned about thermal stresses and fuel cracking. So then our temperature limit is about 1600 degrees Celsius to avoid fuel cracking.